Today we're going to look at the second half of section 9.4. We're still working with arithmetic series, and again our goal is to define them and to find their sums. The new thing today is we're going to look at something called summation notation. It's a way to show that we are adding up all of the numbers in a sequence without writing out all the numbers and putting all those little plus signs in. Okay? So in our summation notation, it uses the Greek letter sigma. So this kind of a capital E looking type letter is the Greek letter sigma. Okay, and what you will have is an explicit formula for your sequence in this position, and then you have a lower limit and an upper limit. That tells us how many numbers we're actually adding together. So in our example over here, we have from n equals 1 up to 5. They're telling us we're starting with the first number and going to the fifth number in our sequence. And we want to add those up. And then this 3n plus 1 is giving us the formula that would generate the numbers in that sequence. So for an infinite series, summation notation would show an infinity symbol as the upper limit. To find the number of terms in a series written in summation form, or sigma form, subtract the lower limit from the upper limit and add 1. Now it's pretty easy when we start with a 1 here to say, oh, I'm going from 1 to 5, that's just 5 numbers. But let's say we had a sigma symbol and they said, let's start with the 10th term and go up to the 53rd term, okay? To figure out how many numbers we're actually adding up, we would take 53 minus 10 and then add 1 back in because we have to count both the 10th term and the 53rd term. So 53 minus 10 would be 43, add 1, we're adding 44 numbers. So we'd actually use an n value of 44 in our formula. If the explicit formula for the nth term in summation notation is a linear function of n, so remember, think of that mx plus b kind of a format. All right, but in this case, instead of x, we'd have an n. So things like 3n plus 5, right? That would be a linear function in n. If you have that kind of an explicit formula, it means your sequence is arithmetic. The slope of the linear function is our common difference. So in this case, we would know that our common difference here is that 3. To find the sum of an arithmetic series written in summation notation, find your first and last terms by simply plugging in a 1 and an n into our explicit formula. And then use our summation formula that we learned yesterday, S sub n equals n divided by 2 times the first plus the last, to figure out the total. All right, so let's look at our first example here. It says we are going from n equals 1, and that's an equal sign, n equals 1, it's a little blurry, up to 70. So we're counting from 1 to 70, that's 70 numbers. So we are looking for the sum of 70 numbers. Then we need to know our first and our last numbers. So to figure out what to put in parentheses here, we need to figure out a sub 1 and a sub 70. All right, well, a sub 1 is simply what we get when we plug a 1 in. So 5 times 1 plus 3 would be 8. So my first number in my list would be 8. My last number is just what I get when I plug a 70 in. So my 70th number would be 5 times 70 plus 3. Well, 5 times 70 is 350. Add 3, we're at 353. So that goes in as my last number in my list. And now we simply calculate this. 70 divided by 2 would be 35. 353 plus 8 would be 361. Now, you don't have to simplify it like that. We could actually, let's grab our calculator here. And we want 70 divided by 2 times, so we can do parentheses, 8 plus 353. All right, we can type it in just like that. we get 12,635. All right, so that's the sum of all 70 numbers in that series. For the second one, again, notice that we have a linear expression, kind of like mx plus b. That means it is arithmetic, and we can use our arithmetic summation formula. We need to know first and last numbers. So, again, this is a little equal sign. It's blurry. We're going to put in, to find the first term, we're going to put in a 1 in. 3 times 1 minus 8. Well, 3 minus 8 would be negative 5. We then need to find our last number, which would be what we get when we plug the 40 in. So 3 times 40 is 120. Subtract 8 would be 112. So I want to find the sum of all 40 numbers. I take 40 divided by 2, and then I multiply to the sum of the first term, negative 5, plus the last term, 112. So again, if we grab our calculator, we have 40 divided by 2, which again you could simplify to just be a 20, times negative 5 plus 112. And we get a total of 2,140. All right. So 2 more examples. Again, in both cases, we have linear expressions for our explicit formula. Since this is linear, it means it's an arithmetic sequence of numbers, so we can add them up using our summation formula for an arithmetic series. All right, we start out with n equaling 1, and we're going up to 30. So we need to find first term and 30th term. So let's plug a 1 in. Negative 2 times 1 plus 1. We get negative 2 plus 1, which is negative 1. Putting a 30 in, we have negative 2 times 30 plus 1. So negative 60 plus 1 would be negative 59. All right, adding them up. The sum of those 30 numbers would be 30 divided by 2 times the sum of the first and the last. So negative 1 plus negative 59 is negative 60. 30 divided by 2 is 15. So we're taking 15 times negative 60. Our total would end up being negative 900. All right, go ahead and pause the video and try the next one, and then turn it back on when you are ready. Okay, let's check. Let's figure out our first term and our 26th term. So we plug a 1 in. 1/2 times 1 minus 5. Half minus 5 would be negative 4.5. Plugging a 26 in, half of 26 would be 13. Minus 5 would be 8. All right, so your total, the sum of all 26 numbers, would be 26 divided by 2 times the sum of the first and last numbers. So 26 divided by 2 is 13. Negative 4.5 plus 8 would be 3.5. 13 times 3.5 should end up being 45.5. All right. So you can take an arithmetic series and put it in summation form as a shorthand way of writing it. The first thing to do would be to figure out what is the explicit formula, because remember in our summation notation we need to have the explicit formula here. And then we have to figure out, we're going to start with n equaling 1 and figure out how many numbers we have in our list. What's our upper limit, our total number of terms. All right, so looking at our first example, we are adding 5 each time. So it is arithmetic. Our common difference is 5. We need to find our explicit rule. We do know the common difference. We can actually count our terms. 1, 2, 3, 4, 5, 6, 7. We know there's 7 numbers. So I know that n equals 7. And we need to figure out the rule for this. Okay, so a sub n, our generic formula for our sequence. We take our first term, which is 6, plus n minus 1 times our common difference, which is a 5. All right, distributing, we've got 5n minus 5 plus the 6 would end up being 5n plus 1. So now we can plug things into our summation notation. So we're going to have that sigma, which is kind of like a capital E looking thing. And we are starting with our n value equaling 1, and we are going up to a total of 7 numbers. And then we simply dump our explicit formula in front here, 5n plus 1. So that would be a shorthand way of writing it instead of putting all of those numbers in our list. All right, let's try another one. We do know that our first term is a 5. We can figure out our common difference because we are taking 5, then 2, then negative 1. 2 minus 5 is negative 3. We're subtracting 3 each time. What I don't know is my n value because there's this dot, dot, dot in here. I don't know how many numbers are being skipped over. So let's work back and figure out what that would be. Let's start with our explicit formula. All right, a sub n equals the first term 5 plus n minus 1 times our common difference, which was negative 3. So 5 plus negative 3n plus 3 would be negative 3n plus 8. That is the rule that I'm going to be using and what I'm going to place in my summation notation. But we have to figure out how many values, how many terms we have in this list. So let's use the fact that we know our last number is negative 22 and use that to help us figure out what that n value is supposed to be. All right, so I put a negative 22 in for a sub n, and I'm going to work back and solve for n. I'm going to subtract 8 to the other side. That gets me negative 30, which means n would have to come out to be 10. So there must be 10 numbers in my list. Now remember that n has to be a positive whole number. If you're getting n values that are decimals or negatives, something's wrong. Because remember, n, you're just counting how many numbers are in the list. So it needs to be positive whole number. All right, so my final piece here, summation notation. I'm starting with an n value of 1, and I'm going up to the 10th term. It says I'm adding all those up, and my formula to generate the numbers is negative 3n plus 8. Okay, that formula goes in there. All right, so we've been focusing on arithmetic series. I do want to point out that even if the series is not arithmetic, we still can find the sum. It just means we have to actually calculate all the numbers in our list and then actually add them up with our calculator. So it works nicely when we don't have a lot of numbers in the list. Like here we're saying n is starting with a 1 and it's going up to a 4. So there's only 4 numbers in my list. So let's list this out. 1, 2, 3, 4. Let's figure out what those 4 terms are. All we have to do is plug our numbers in for n. So our first term is 1 cubed, according to the formula, which is just a 1. Our second term would be 2 cubed, which is an 8. Our third term would be 3 cubed, or 27. And our fourth term is 4 cubed, or 64. And we just want to add those up. All right, so 1 plus 8 is 9. 9 plus 27 is 36. And 36 plus 64 would be 100. So our total here is just 100. Now the reason I know that it's not arithmetic is that my formula here is not linear. Okay, it's a cubic equation. our cubic formula, it is not in that mx plus b kind of format. Okay, same thing with our next example. N minus 1 quantity squared is not a linear expression. If we actually multiplied that out, n minus 1, it's going to be quadratic. So this is not arithmetic, but we are only looking to find 5 terms, so we can figure out what each of those numbers is and just add them up. All right, so let's start by plugging a 1 in. So this first term would be 1 minus 1 squared. Well, 1 minus 1 is 0. 0 squared is 0. Our second term would be 2 minus 1 squared. 2 minus 1 is 1. Squared is 1. Our third term, 3 minus 1 squared. 2 squared would be 4. Fourth term would be 4 minus 1 squared. So 3 squared would be 9. And our fifth term is 5 minus 1 squared. 4 squared would be 16. We're going to add those up. All right, we can make this easier on ourselves. We know 1 and 9 add up to 10, and we know 4 and 16 add up to 20, so our total must be 30. All right, so let's take a minute to review the things that we've covered so far about arithmetic sequences. Let's start with our recursive formula. Remember, recursive formulas always start with our first term. So we're going to list whatever that first term is. And then our nth term always takes the previous number and adds whatever that common difference is. All right. Our explicit formula says a sub n equals first term plus n minus 1 times our common difference. We talked about the arithmetic mean. So finding a missing term in between two consecutive numbers, we simply add the two numbers up and divide by 2 or take their average. And then we also looked at our summation formula. S sub n equals n divided by 2 times the first term plus the last term. All right, so our next example says write the explicit formula and recursive formulas for the following arithmetic sequence and then find the 14th term. So our recursive rule, we know that our first term is 3. And if we look at what we're doing to go from one to the next, we're simply adding 4, so that our d value must be a 4. So our next term will take the previous number and just add 4 to it. Okay, that is our recursive rule. Our explicit rule says take the first term, which was a 3, and add n minus 1 of our common differences. So we're adding a 4. We get 4n minus 4 plus 3. Our recursive rule would be 4n minus 1. And then our last piece, we are trying to find the 14th number. So plug it in. We're putting 14 in there. So 4 times 14 minus 1, we end up with 55 for the 14th term. All right, finding the arithmetic mean for this missing term. We need to add the first and the third terms together and then average them out. So 5 plus 19 is 24. Divided by 2 is 12. Our missing number here should be a 12. All right, the last example says to write an explicit arithmetic rule and find the 10th term. So we know our first term is 4. We know our fifth term is 40. So we can use that. We can say our fifth term takes our first term and then adds 5 minus 1 of our common differences. Well, we don't know what the common difference is, but we can figure that out. Our first term is a 4. Our fifth term is a 40, and we know that we have 4 of these common differences. Subtracting 4 gets us 36, and dividing, we know that d is 9. So now we can write our explicit rule. a sub n equals our first term, which was 4, plus n minus 1 of these common differences. Distributing, we've got 9n minus 9, or 9n minus 5 once we've combined like terms. Then we can find our 10th term by simply plugging a 10 in. 90 minus 5 would be 85. And then if we wanted the summation of those 10 numbers, we can say the sum of 10 numbers is 10 divided by 2 times the first term, which was 4, and the last term, the 10th term, was 85. And our total now would be 445. All right, so you guys are going to work on 9.4b worksheet. Let me know if you have questions.